Hello, everyone. My name is Devost. I'm a resident astronomer at Canada-France Hawaii Telescope, and I'm presenting a poster during this meeting about the scientific impact of CFHT. And I present a few metrics. Some of them were presented in Natan's talk, and I focus on the instruments, the observatory, and the papers. And I hope that this poster will help you understand how productive CFHT was in the past to make it even more productive in the future. Thank you.
Hi everyone, I'm Khatu. I'm a resident astronomer at CFHT as well. And this slide is on Shadow the Scientist. It is an educational outreach initiative that we started this year at CFHT. So we have joined the community of other Mauna Kea observatories who already run Shadow the Scientist. We did our first two events in February and March. First one was for the Mauna Kea Visitor Station, the 9,000 feet facility on Mauna Kea. And the second one was for a scholarship group, a student group from India. So this is basically, it has a broad audience. It is open to users, student groups, indigenous communities, and the general public. I have QR codes over there, but my poster is in the poster room number 2. So if you want to know how you can make use of the program for your students or other communities, please come talk to me. Thanks.
Hi, everyone. I'm Folsom, working with Khatu Observatory in Estonia. And my poster is about this SpecPol Flow project. So this is a open source analysis tool set for spectropolarimetric data. It's more or less designed for using with Espidons and Spirio here at CFHT. The goal is to provide a set of tools for doing the kinds of analysis that people commonly do. So there's like LSD, making line masks, this sort of thing. We have an extensive set of documentation on our website. The overriding goal is to make this relatively easy for people to just pick up and use. So you can just use pip to install. If you're familiar with Python, you can run pip install and get the package and then start playing with the tutorials on our website. I encourage everyone who's interested in this to check it out.
Hi, I'm Diez. I'm a PhD student at Université de Montpellier in France, supervised by Pascal Petit and Julien Morin. In this poster, I present the selection of plateau target focusing on M and FGK dwarf, for which we contain polarimetric analysis. Using the Doppler imaging, we produce preliminary magnetic maps. Here, for example, you can see one for an M dwarf, showing the different components of the magnetic field. The different preliminary magnetic maps reveal a diverse range of magnetic topology, as illustrated by 2 examples in my poster. This work is part of long-term monitoring to study the evolution of stellar magnetic field. So, if you'd like to know more, my poster is at spot number 5. Thank you.
Hello, I'm Neil Cook. I'm a researcher at University de Montréal. I don't really need to sell Aparo because if you're using Spirio data, you're already using Aparo. But if you want to talk to us about feedback, about suggestions for the future, or just to know what we're doing next, please come talk to me or Etienne. Thank you.
Hey, hi everyone. I am Ayan from the Queen's University. I'm a PhD student, and here in my poster, I am showing results from a specific M dwarf. So this is special because I observed it in radio wavelengths, and for specific phase of the nearby planet, orbital phase, I saw the polarized radio emission, which we think is from aurora, from star-planet interaction. And I followed it up with Spirio, and got the magnetic map of this and saw a rapid change in the magnetic field in just 3 rotation cycle. Both the field strength, geometry, everything changed. And based on those map and estimate, I constrained the planetary magnetic field, keep the lower limits of the planetary magnetic field. If you want have any question, please check my poster and ask me. Thank you.
Hello, everyone. I'm Tingli, and I want to take this opportunity to highlight two programs that are instrument that have been working on, not really directly related to CFHT, but I think can be associated. So on the left, you see is how we have been doing high precision photometry with ground-based instrument to measure the giant and dwarf stars with color information. And the bottom left, you see how we have been using photometry to measure the metallicity with broadband. And we can confirm all of the stars in the nearby dwarf galaxies are metal pool. And on the right is another program you may heard more talk later called the Diez Dark Energy Spectroscope Instrument. We just had our first big data release for 4 million stars with spectra and stellar parameters all released. So if you're interested in any of those, feel free to talk to me.
So hi, my name is Poitras. I am a master's student at Université Laval. So over the past year, I've been studying the incredible filamentary nebula of M87, which is the central galaxy of the Virgo cluster. So while the inner filament are well explored, the outer filament are remaining mystery, and this is where our work comes in. So we want to, with UCTL data and Megara, we want to do a velocity map of the entire filamentary structure. We use this to probe the turbulence of the gas, so how it moves, where the energy comes in. And we also look at the molecular gas and the X-ray emission, and we found a strong correlation with iron light gas, even though we have a little bit region that are a bit different. And yes, if you have any question or you just want to talk about those filaments, come here at poster 10. Thank you.
My name is Mary Oksala. I'm a faculty member at a college called California Lutheran University outside of LA. And I've been using CFHT for a number of decades to do work on magnetic massive stars. And so in the last 9 or so years, we've been working to use CFHT and Espadons, as well as TBL, Narval, and HARPS to study what happens to massive magnetic stars when they get a little bit older. And so we're looking for changes that happen as they change their radius, as they move through different kinds of evolutionary phases past the main sequence. And so if you're interested in learning a little more about that, I'm poster number 11. Thanks.
Hi, everyone. My name is Alexandrine Lheureux. I'm a PhD candidate at the University of Montreal. And this week, I'll be presenting some very exciting results from the Spirou Legacy Survey. So we followed up with radial velocity the TRAPPIST-1 system, which is very famous for its 7 terrestrial planets in orbit around an M8 dwarf star. And with Spirou, we were able to obtain the first radial velocity detection for that system, confirming the masses that were previously inferred only from TTVs. So if you're interested in TRAPPIST-1 or radial velocity or Spirou, you can come find me at poster 12.
So hi everyone, my name is Glasman. I'm a master's student at Université Laval, supervised by Laurent Drissen and Nicole Saint-Louis. I'm interested in supernova remnants in nearby dwarf galaxies. So the goal is to study those objects evolve in low metallicity and high star formation rate regions. So my main galaxy is NGC 4449. It's quite interesting because it has a high level of diffuse ionized gas throughout the galaxy. So it prevents us from only detecting the objects using line ratio emission line. The interesting thing with CTEL is that we are able to very effectively see the expansion of the objects. And the second galaxy I'm studying is IC 1613. It's T. Okay, cool. IC 1613, at the beginning of the year, there was only one supernova remnant identified in the galaxy, and we were able, using CTEL data, to identify a second one. And here we see the expansion of the bubble throughout many channels in the CTEL data cube. So that's...
Hi, I'm Christy Erba. I'm currently stationed at Space Telescope Science Institute in Baltimore, Maryland. One of the things that I work on, thanks to CFHT, thanks to Espadon at CFHT, is characterizing the magnetic fields of slowly rotating O-type stars. So this poster is about one of those efforts for the most recently discovered magnetic O-type star, HD 54879. It's an O9.7 star with a complex magnetic field, and yes, it is actually complex. If you would like to learn more about that, please see the poster. And I would just like to take this opportunity to thank CFHT for continuing to invest in long-term monitoring efforts like what we do for HD 54879, NGC 1624-2, Psi 1 CMA, HD 108, and a whole slew of other awesome stars long-term monitoring efforts like this really do provide us unique and important insights into the structure and topology of the magnetic field. And so this poster and many others, projects and posters that are discussed here are thanks to that long-term investment. And yep, that's it. Hello, my name is Natan. I'm a graduate student at the University of Delaware, and my project is looking at the MIMES survey B star sample. So this was 214 single B stars, and the goal of this work was to look at our magnetic incidence rate and also to look at our detection limits and compare that against previous results for the O star sample in the MIMES survey. So come to poster 15 if you want to hear if it's still 10% for massive magnetic stars. Thank you.
So, hi, my name is Anne-Sophie Roy. I'm a master's student at University of Laval under the supervision of Carmel Robert. I study star clusters in the irregular galaxy NGC 4449 with SETEL data. I have detected more than 2,000 candidate clusters using the continuum maps of the SN1, SN2, and SN3 filters. The young clusters are broader in SN1 and can be associated with their respective H2 regions that we can see with the H-alpha map. To determine our physical properties of our clusters, like the age, the mass, and the extinction, will be determined using stellar population synthesis methods and will be compared to the Legis catalog that is based on the HST images. But first, I want to associate my clusters with the Legis clusters and to compare our spectra with theoretical models based on the Legis results to show how the height of the continuum can match the slope of the SED2 and the presence of absorption features and nebular emission features. Thank you.
Hello, everyone. I'm Véronique Petit from the University of Delaware, and I brought a poster from my group because, as you know, massive stars, OB star, BA star, have magnetic field. We don't know where the hell they're coming from. So an interesting thing would be to figure out the initial magnetic field function, which we call the IBF because IMF was already taken. Bummer. But the problem to try to observe young OB stars to try to figure out this IBF is that they're often enshrouded in a natural cocoon. And they're very obscured. So maybe infrared could help because infrared can actually go through. But, think about it. Observing a massive blue star in infrared sounds a bit silly, but maybe that's the only way to go forward. So before we decided to test it out by observing with Spiru some really known iconic magnetic massive stars to see if we could recover the magnetic field of these stars. And if you're dying with anticipation, the answer is yeah, pretty much. So, see poster. What was my poster number?
Hello, my name is Patrick. I'm a graduate student at the University of Delaware. So as we've heard from previous poster talks, the well-known result is that 10% of massive stars are magnetic. However, this 10% magnetic incidence is seemingly not present for a subset of massive stars known as classical BE stars, for which there is a 0% magnetic incidence. These stars are very rapidly rotating, upwards of 88% of their breakup velocity, and also have emission lines due to a Keplerian decretion disk. So the purpose of my project was to determine if this 0% magnetic incidence is true or if it's simply a product of their physical parameters that make detection and characterization of these fields very difficult. So if you want to know how we did, come check out poster number 18. Thank you.
Let's give applause to all the speakers of this session.